Okay, my friends, Roger once again talking about physics, and before I even start, I'm going to show you that I can prove what I'm saying. This is a normal wave coming through the air of pulsed red laser, creating a wave because it's a dipole particle, which I will show you in great detail. And what did we do? We collapsed that wave. And why did it collapse, Roger? Well, it collapsed because the particle that was pushing this wave forward was sucked through this venturi and accelerated. So what am I saying? We crushed this wave by acceleration. Two things not supposed, well, one of them they say Einstein said it could crush the wave, so we did it. The particle is not supposed to be able to go faster than the wave, which it did. And then it backed up here and separated, creating fission and fusion. All of this I will show you, but let me show you what their claims are. But before we do, I want you to know, I have been working on this new atomic theory, and it's my claims are that there is nothing but dipoles. This is just a little, I'm going to lay it all out in pretty good detail, but it's pretty well, it's simple, very, very simple. The black particles never change, and the other colored particles, they can get fast and slow, and I can divide them, and we can, Higgs fields and all that. And this is the new nucleus model. It's because there's different charge zones. I can go through all of this stuff, and it accounts for every single thing there is. Every single thing there is in the physics world. So if you want to be a physicist, now's a good time because it's wide open. Good morning, my outstanding friends. This is going to be a trip which you will never forget. What are we talking about today? November 27, 2022, this comes out. Completing Einstein's theories of particle physics breakthrough. Well, this is at the University of Osaka in Japan, and I've always considered them to be very ethical researchers. So let's see what they have to say about my comments. More than a century after it was theorized, scientists have completed Einstein's homework on special relativity in electromagnetism. Well, let's see what they claim to have done, and I claim to have done it long ago. Okay, this is what they did. Osaka University researchers showed the relativistic contraction of an electric field. A field, we all see these fields, they show field lines surrounding electric particles. But they show the contraction of that field produced by fast-moving charged particles, as predicted by Einstein's theory, which can help improve radiation and particle physics research. Well, they're talking 100 years ago, but now scientists from Osaka Institute of Laser Engineering, laser, utilize ultra-fast electro-optic measurements. All that is cell phones. For the first time to visualize the contraction of the electric field. I'm not kidding you. Surrounding an electron beam traveling at near the speed of light and demonstrate the generation process. Let me show you. I've been doing this for 7 years, showing this exact same thing. Okay, this is very, very simple. A muon strikes a semiconductor. Well, what is a semiconductor? It's called CMOS. It underpins a smartphone camera. It liberates an electric charge. As soon as that particle, and it's instantaneous. I mean, there's no high speed this and that like they're talking about at Osaka. The electric charge creates a signature in pixels. It can be logged, stored, and analyzed. Exactly what we did. Cosmic rays emanate from, they think cosmic rays come from only beyond our solar system, and you can see them, though, in their particle colliders. Well, we collide light and crush the fields. We do it much more effectively, efficiently, and we can analyze it much better. But this is all talking about muons using smartphones to pick up these cosmic rays, which are muons. All right, so this is just sort of hyperbole. Ultra-fast electro-optic measurements, that's just nothing more than CMOS. And also, CERN is bragging about their CMOS now. I tried to explain this to them. I did, I'm not kidding you. This was in 2015. I tried to explain to them that you could use a smartphone to detect the particles of light that we were showing. And I'm going to show you those right now, because we split them. We did everything they wanted to do in 2015 using the same technology that they're touting now. Okay, my friends, I'm trying not to get too excited, but this is the day that I hope finally someone will pay attention, because I'm going to show you the contraction of these waves using cell phones, which use the CMOS, the same thing that everybody is, oh boy, we can use CMOS now. Well, you could use it 8 years ago, 7 years ago. Most of everything we know about the universe is based on his theory of relativity. However, a portion of it has not been experimentally demonstrated until now. Well, I can demonstrate that virtually none of it is correct. Virtually nothing he said was correct. Well, I can't say it that way. That just sounds really harsh, but, well, you see what you think was correct and what wasn't correct. How about we do it that way? The first thing you have to understand is no such thing as a vacuum. There's no vacuum anywhere, and you cannot create a vacuum. It's impossible. Everything, even blank space, has electrons in it. It has electrons in it. That space is filled with particles, not completely packed. They're as far apart from each other as they can get, but they're still in there. You cannot stop it from being in there. That's the first thing that creates the problem with Einstein's theories. He based everything on a perfect vacuum, and there is no perfect vacuum. You can't have light going through a perfect vacuum. There's going to be particles that are in there that are electrons. You cannot stop it. In no way in the world can you stop it. They're eventually going to slow down as they push through them. Let me show you the effect. Now, first of all, empty space isn't empty. This is by Don Lincoln from Fermilab. And I talk about him a lot because I interacted with him and I showed him the particles that we saw, and I'll show you right in a second. Same particles he found. Now, he's saying that empty space is not empty. It's filled with what he calls a quantum foam, which is these electrons. They're just there. And now these are the particles that we found that he was looking for in 2013. Well, they found them. But they found them as the tiniest particles that exist in the debris that they created by smashing huge particles, gigantic tons, billions of particles together, and then they saw all kinds of debris. It took them 10 years to dig through that debris and finding these tiny, tiny little particles, saying, yep, that's it, that's the smallest ones that exist. Well, we found those using our light research, using the pulse lasers, exactly like Osaka. Okay, using cell phones, we captured light from a pulse red laser beginning to accelerate. That's why we can see the glow of the wave. This may be hard for you to see, but there's 2 black balls and 2 white balls, or red balls, basically. Now the one in the front, you see how it's real glowy, and it's glowing down here, real glowy looking, and the one in the back is not. This is because this is the way a photon, which this is, moves through the air. The leading glowy part gets glowier and glowier, and then it flips to the back, and this one comes to the front. So it just makes a spin and a spin and a spin. And they charge up very quick and spin very quick. Now, this is all particles being concussed because they also have electrons. Everything has electrons. So when you force something into somebody else's regions, they glow and you glow more because you're the pusher and they're the shover back. I call it push to shove. This is the push, that's the shove back. This is going to glow like crazy. These are just going to sort of work their way out now. So here's the particle. This is the wave. Everybody's always been looking for it. Now, let me show you what CERN and Fermilab say, because this is identical to what they see. No difference whatsoever. I'm going to explain this in relation to what Don Lincoln shows. Okay, so what am I showing you and what is Fermilab claiming? They're claiming these are the smallest particles they can find. This one has virtually no mass, and this one is just a bowling ball. It's just solid, fixed, they call it. And they call that a point. It can get big and get small. We found those. Now, when I was just showing you, and I'll show you again, the electron, an electron is not just a glowy, pushy, burny part. static, lightning, electricity. No. It is also got a dark matter part, which they call a muon, and there it is right there. So this is literally the electron we always thought was electron. This is the dark matter, and it is gravity, and it is the muon, and it is attached to the electron. It's the carrier. This has no mass to it. This is the thing that carries. But this burns like hell. And that's, I think it's cold. I'll explain the whole thing. But these are the two parts. That's all exists. Nothing else exists, just those two. And they say, yeah, we can find these as the smallest one, but then we got all kind of particles. Because they're hitting things like this, hundreds of them together, bam, at the same time. And they get all this crazy stuff. Every now and then they do get one, yes. They get one just like that. And it's this right here. It's right in between the two. There's some red, there's some black. No question. Now, when you put two of them together, you have a photon. So you have two blacks and two reds, and that's what a photon is right there. Now, I'm going to show you these. I'm not just guessing. This is absolute fact. Okay, my friends, so let's take this one piece at a time. I say there's a complete new model of the electron. And everything there is made up of the electron, which consists of these two parts, which is these two parts right here. Exactly as Fermilab says. They're the smallest two parts they can find. Now, you take these two together, which makes an electron. It's static electricity, it's lightning, it's actually heat. And these glue to other particles. They just stick because this attaches to the dark part. The electron always wants to glue on to a muon. They want to glue, ooh, that's cute. They want to glue on to a muon. Remember that. An electron glues on to a muon. Now, what about a photon? Well, a photon takes the electron that was glued onto the muon and it adds two of them together, which is 2-bar magnets. All right, so here, what do we have here? We have 2-bar magnets. They come together, they stick. They're glued together. Now, as this goes through the air, and I think I showed you already, it charges up, and then it will flip, and then this one will charge, and then it'll flip, and then this one will charge. That's called the muon wobble, and it always polarizes to Earth. So they'll always be in this plane. They're never supposed to barrel roll. However, we did make them barrel roll by pushing one against another. That's the only time I've ever seen it. And I'll show you all of these things in great detail. Just about in 5 minutes, you'll see all this. We've seen the tau neutrinos. This tau neutrino is faster than light. I could show all this. This is the particle that John shows here. The black never changes. Case closed under that. It weighs 0.000545 atomic mass units. That means that if you multiplied that times 1835, you would end up with 1. 1 is what they call a proton. And there's a certain thing called a periodicity, periodic chart. And for some reason, and I think I got it figured out, they will only be stable at certain intervals of particles. They thought it was 1, 2, 3, 4, 5, or right up the line. No, it's 1836 or so, and then it's 7,350 or so particles here, because every single proton is 1,836 electrons. All right, and the protons are dipoles. Everything's a dipole, 100% dipoles. Now, a muon, a neutron, which is really, they call it a neutron, but all it is if you had 1835, you're unstable. You want one more. You want to give one up or take one on. A neutron has an even number, 1836. And it actually, if they had you look at the weights, it weighs exactly that much more than a proton. So it obviously has one extra electron. So now, I'm showing you all of this stuff, and here's what happens with the red part. Exactly what Don Lincoln says. It has almost no mass. It's like hollow. It's just almost nothing there. But it burns like hell with a field. It's what I'm going to call the electron portion, electron neutrino. It's almost zero, very small. It's extremely hot. It's squishy. It can pinch together. And it's pushy. It pushes everything apart. And when we start talking about electron volts, you're down in this very, very small energy value. However, one electron volt can go way up to millions of electron volts and even higher if the field is crushed to an extent that it's atomic. I mean subatomic nuclear. I created subatomic nuclear explosions, and you will see them right now. Okay, now, by the way, when I said I created this is not my pictures. This is from Rod Warren, and I call his Venturi because he created this just by accident, just playing around. He didn't know what he had. I do the atomic part, and when I saw it, I said, Rod, you created something that divided light. You did all this stuff, and he's, wow. So he worked with me for, I don't know, a couple of years at least. And shown, everything I asked him to do, try this, try that, and he did all these things. And I have all the evidence to show we divided it. We created fission, fusion. These are the same particles. These are the same particles that Don Lincoln wanted to see. And here they are in light, not in collisions of protons that smash the hell out of everything. And this is the separation of those blacks and whites, just like they wanted to see it and have seen at CERN and Fermi, but it means nothing because they have just a splash of debris. And they say, wow, we can see these muon and electron neutrinos together. That's the black and the white. All right, there they are. Same ones that Don Lincoln had in his point particle article. Point particle article. Boy, I'm getting rhyming timing today. Anyway, now, then it blows down to the muon, just goes on its way. See it? It fell off. It cannot stay with the electron because the electron went to a shower mode. And this happens due to a change in the density of what it's hitting into. And the change was because of the Venturi. I'll explain all this stuff, and it's going to take some time to do. But here we are. Here's the wave contraction. They said, oh boy, we figured out how to make the wave contract. Yes, there it is right there. I showed you the big wave. I showed you where the particle would exist in the front of it, creating a magnetic field, so you have particle-wave duality. This is acceleration. So here I'm proving Einstein was right and wrong. You can crush the particle wave, yes. And there it is, being crushed, it's being deformed because we're exceeding the speed of light. That was the speed of light before. And now we have exceeded it, and now it's going to slow down. And they say this is exactly what they see with the neutrinos. They're almost the speed of light, and then they're this and that. Well, this is beyond the speed of light, and it's a tau neutrino here. It has two blacks and one white. Here it turns into a photon, is two blacks and two whites. Here it separates to the black and the white separate and go on their own way. And then here the black and the white come back together. And I can show every single one of those events in extreme detail right now. All right, before we go further, here's the things you want to remember. Back here, there was just light. You just barely could see it, and it was almost nothing. Because there's the same waves that is right here are everywhere. But you can't see them because they're not concussing. This one here is exactly dead center into the Venturi. That's the only reason you can see that wave. You'd never see it. And the one I showed you before that just was not accelerated yet was just beginning to break into acceleration. Rod did such a fabulous job at capturing these. It's just unbelievable how, and he put a lot of work into it. I have literally hundreds of different pictures from different experiments we did. Now, we know the wave is collapsing, there's no question, and the only reason is it's just like a jet fighter getting past the speed of sound. It's breaking the light barrier. But what happens then? It stacks up on itself, and then it slows down because it's push to shove, push to shove. So before it was just going and almost nothing was in its way. Now they're stacking up. So it's bang, 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 bang. So it's good. Now it's bang up. The blacks are too big and too solid, they separate from the white and then they jackhammer the whites through here. That's what's given us our increase in energy, is the jackhammer effect. That's what I'm seeing, because it's a speed up of light. So Einstein was wrong. It can speed up, and I can show you it slows down too. It speeds up, and then it's because of this medium it's coming up against. The same thing with heavy water. It's boom, and then it slows down a little bit as a photon, which, you know, it's still the speed of light, but it's, you know, there's a very, very small difference, it appears to me. And they say that. They say the neutrino is almost identical to the speed of light. Anyway, so you had your neutrinos here, which is a tau. You have your photon here. Then you have your muon and electron neutrino here as a pair, and then they explode at the venturi, completely explode. And then they have to come back together. The white is gone from the black here. It's absolutely on its own. So it has to come back together. Now let's see all of those events occurring. All right, and don't forget, I've shown exactly what they've just been talking about. However, I've shown that Einstein was wrong, and in the case of a collapsing a wave, he was right. And the idea that there is a vacuum anywhere is wrong. And Fermilab knows that. They say there is no such thing as empty space. Correct, Don, correct. Okay, before we go any further, and I can show you, I have details coming out of my ears. The only thing that exists are these two particles, the black and the white. And then you add them together and you start to grow light, and then you start to have nuclear particles, and then you get your nucleuses, and then they keep getting bigger and bigger. And I believe they're constructed like eggshells. I'll show you, and I believe the first pretty stable egg formation is the hydrogen, and the dark particles are pushed to the center, and the white ones surround it. And I'm going to draw you out all the diagrams I have of the shells. This gives you dipole, and you have your shells. You still have your shells, but it's because they're constructed with zones of black attractive gravitational particles, and then a white coating, and then there's another black, and then there's another white. It's like zebra striped coming off. I'll explain this and you'll see, because the weights work out, everything seems to work out, and the zones, they call them dipole molecular moments, and it's going to take a little discussion to get through that, but the bottom line here is I don't see why we can't get free energy. We're creating an extreme increase in the value of energy. Energy is valued at how much glow and luminosity you create. And it takes so much energy to make luminosity. It takes a lot of energy to make something glow. Well, this didn't take any energy at all. All we shot was the laser, but we put it through a device called a venturi. And it was constructed in just an accidental way by Rod Warren. It's called now the Warren effect, the Warren Venturi, and it's just a round circular pin, two of them, one side by side. The light goes right through the center, and all of the particles have to come in, and their fields crush, and they can't get back out because the black ones are slamming them through, and out they go. Elegant device, elegant, elegant, elegant. And if this is true, in this area right here, if we can harvest this right here, right there, we should be able to get free energy coming out of our ears. This is fission. We broke apart the black and the white, and this is fusion. I don't care how you cut it, that's what it is. And that's the muons, and these are electron neutrinos, exactly identical to what CERN and Fermilab look for and see, and they call them the Cherenkov radiation creates these electron showers and sterile muons, and they come from muon neutrinos and electron neutrinos, which was the black and white glued together. So I don't know how many times I have to say it, but that's what it is. And here's the two particles that they're supposed to come from. The Fermilab found them, and so does CERN. They know they're there, but when they smash things together, they just get debris, so they have no idea where they came from. I'll show you them, all of those neutrinos in one picture. Watch. All right, now check this out. This is just as the light is starting to accelerate. Prior to this, you don't see anything, because this is light up here too. You don't see these up here, you don't see them down here. The only reason you see these is because they're right in line with the Venturi. That's the only reason, and they're starting to concuss. So they start out with the tau, which is actually faster than the speed of light, and then they start to pile up on themselves, banging against the Venturi, so it's boom, 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 boom. So they're slowing down a little bit. Right? I believe. It looks like to me they're slowing down a little bit. Or maybe they slowed down here. I'm not sure. But this is the tau. And then we have the photons. And the tau is black, white, black. Black, white, black. See it? Then we have black, white. The two electrons together, which electron neutrinos with the muon neutrino attached, two of them together. And this one here now has already flipped. You see? The black on the bottom is in front. Now this time the black is on the top. That's just upspin and that's downspin. All right, the glowy one will charge up and then it'll flip. And I think I've shown you that, or I will. Here's the Venturi. There they just completely divide and they just go on their own separate way. And the white has to slam through the Venturi because the black keeps pounding it through. Okay, my friends, this is fabulous. I just got this in about completing Einstein's theories, particle physics breakthrough. And they're doing virtually exactly what we did. The contraction of the electric field produced by fast-moving particles. They finally found this. Well, we showed this a long time ago. Let me show you a contraction of a field because of a fast-moving charged particle. Okay, this is light coming through the air. We're using CMOS technology, top-of-the-line technology to photograph highly luminous particles. That's what you see here. So what we're seeing is radiation from the particle that's creating this wave. It's a particle that has a magnetic field. As it goes through, it creates this wave, which is a magnetic field. That is a magnetic wave field created by a particle that's coming behind it that has a magnetic field surrounding it. That's why it concusses with all these other particles in the gases in the air, which are also magnetic. That's why they glow, because they say, get the hell out of the way. That's what's going on here. Can we show that field crushing? Absolutely. All right, if you can't see that field crushing, I don't know what you see. Before it was a nice rounded field, and now it's starting to accelerate because of this Venturi. And the only wave that's accelerating is this one right here, because it is exactly in line with the Venturi. There are zillions of other waves here. You see one here, one here, one here, one over here, one over. They're everywhere, but they don't radiate like this one, because this one's being pulled forward, accelerating, going faster than the speed of light. These are just there at the speed of light, but they're being concussed backwards, so they glow. Otherwise, you'd never see these particles. You don't see them. You don't see it right there. There's nothing there, nothing there. It's there. You don't see it. This one's here, and you see it because it's being, these are being banged back against them. Now, what's happening here? It's fission. The black particle got away from the white particle, and the white particle showered through, and now they're reattaching. I show this in, yeah, well, I've shown it. And I can tell you what all the phases are. From the light, which is basically photons. They become visible down here, but down here you have tau. Tau is an accelerated, tau neutrinos. They're accelerated light particles. As you can see, they're accelerated. And then they stack up on themselves and they slow down. And they say exactly what they say. They say they're just almost the speed of light, very, very close, which they are. They were at the speed of light, they're accelerated past the speed of light, and now because they're all trying to get through that thing, it's like a mass of people go bang, 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 and they're all, and so you got to slow down. So they slow down that neutrino right there, and at that point, they actually become photons. So here you got black, white, black. Here you got black, white, black, white, like 2-bar magnets. And here they explode. They first go into black and whites, and then they black shadows away from the white at at the Venturi. It can't get through. So it's bam, 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 bam. And here, it just squirts them. And here they reattach, the black reattaches, and I can show all of those sequences of events occurring as they actually occur. All right, this is the pictures from Fermilab. They've seen the exact same particles. They say they have the exact same characteristics I'm talking about. Fixed black particle, gooey, squishy white particle, or green or red or whatever. And that's this photon. And that consists of two bar magnets that are what they'd call gluons. It really were electrons. They just never knew the black particle was attached to the white. The white is the electron. That's the glowy, pushy part. You see it down here? That's what causes all the burny stuff. But it has no mass. The black is 95% of the mass is right there. This is like almost nothing, but it burns like hell. This is that photon made of exactly the same particles they found at CERN and Fermilab, only they find them in debris. We find them as part of our focus of light. That's a focused light beam. That's just light. It's exactly what it is. And down here, you see at the bottom, you see those little red particles in front of that one? Those are making that bottom spin. That's what you'd call bottom spin. And the bottom spin particle is charging up. And as it fills up, it'll flip. And that one will come to the front because it's going to start absorbing, and it'll start doing that. But this one will be behind, and it'll be trailing. The blacks never change. So the black is going to go to here, the black will go to here, the white will go to here, the white will go to here, that type of thing. Now, what happens when it hits a Venturi? Here it's just really starting to concuss. That's why you see it so nicely. When it hits a Venturi, it's case closed. Right? Here it's coming, and we see it right here as that glowy particle. Back here it's the tau. It's a black, white, black, white. Well, you'll see in a second. And here it splits. But this is the key right here. They separate. That's fission, and that's back together as fusion. Exactly what they say at CERN Fermilab. Muon neutrino attached to the electron neutrino turn into the muon all by itself, sterile, and electron shower. And I can show this in green and red, and I can show it happen both at the same time. All right, I'm going to show you red in a second, but it's identical. You see that? That's the tau. Then it turns into the photon, and then it breaks into the black and the white, and it's just getting ready to explode. Now, let me show you the red. Same thing, exact same thing. All right, I might have already showed you this, but here it is again. This is the tau coming through, starting to stack up. This one flipped. You see now the black is behind? This is the same particle. You're taking it all in one shot. And here it exploded and divided into little bits and pieces. So you got tau, photon, muon, and electron neutrino, sterile muon, electron shower. That's it. All right, this is really almost too cool to explain. There's the light wave coming through. I showed you before, concussing all these particles. There's the field being crushed, exactly what they wanted to say for Einstein. We showed that. There's the particle itself dividing and fission and fusion. So I'm saying there was the tau, there was the photon, there's the neutrinos, then the muon by itself, sterile, and electron showers coming back together. Can I show all those things and prove them? Yes. Coming out of here, this white is right here. We're looking into this white. You see it come out of here? Brilliant, brilliant, brilliant white. Well, that's what we're doing, is looking into this. The laser's coming this way. Just a gigantic explosion, because this is nothing more than a Venturi. And a Venturi is nothing more than a pinch point. And the black is just too big to get through, so the black can't make it. It has to go around. Now, the white shower's coming at us. And here they are right here. These are those white showers coming right at us. We're looking right into the Venturi here. And what are we seeing? We're seeing the reattachment of the white back to the black. It's got to get back to the black. You can't have a white without a black. And here you do have that. You have whites without blacks, and it's just a shower of white intensity. Look at it. Wait till I show you another one. I'll show you another shot. It'll blow your mind. Of course, all this stuff should blow your mind. because it's completely different than what you heard in school. But this is the reattachment of the black coming back to the white. And that's at the tip of these waves. You see them? That's where the black's coming back to the white, because that's where the concussion zone is. The trailing particles are trying to catch up, and they're still white hot. You see them? They're still white hot because they're behind. So a few of them pick up a charge to, go back to their black and white state. But primarily the tips are the ones that come back to being normal quickest, which, that's what you would expect. Because here there is just nothing but white. Wait till I show you this other shot. So if you understand what I showed you, this is just a wave, no real big acceleration yet, although it's starting. Right here it's starting. Otherwise you wouldn't see it. You wouldn't even see it. You see there's waves all over here. You don't see them because they're not in line with the Venturi and it's not accelerating. So they either accelerate this way or they get pushed back that way. Either way they're going to glow. This one's starting to glow, pulling right out of this wave, just exactly like they wanted Einstein to. They're claiming Einstein was right. Well, he wasn't right about much. I got to be honest with you. You tell me what you think. But if light is a particle that's a dipole, and all the things I'm showing you, and light can accelerate and it can slow down, I'm showing all that. It can divide, and in space, I believe they do divide quite easily. The Russians showed that in an experiment out there. All right, I'm not just a complainer, I'm telling you the truth. This is the LHC, that's the Large Hadron Collider at CERN. They wanted to use it as a photon collider, but they couldn't figure out how to do it. It says right here, in 1978, it was discussed the prospect of a special meeting. And what happened? They said they couldn't do it. It said these collisions are very clean as we're colliding photons. That's what we use, the light, photons, which are the most, well, in that case, the elementary particles that they know of, the smallest ones they know of, and not composite ones like protons. Exactly. And this is Joan Varela, former deputy spokesman for CERN, who is heading the project. It was first proposed to do this type of physics, LHC, many years ago, but the project didn't materialize then. They couldn't figure out how to do it. And it's very simple to do. I showed you how. And I showed them how to do it too at CERN and at Fermilab. And they shut down CERN to make their particle focus. And they just came back online. Now, I don't know if it was because of what I told them, but I told them, I went to Coursera. I think I'm going to show you something, or I did show you something about how to go and get educated, how to find out what they're saying. Come to me for education, but go to them to see why they're wrong. Because you can't just say, oh, you're wrong, without knowing what they're wrong about and what they're saying. That's why I go to all these different courses. I went to a ton of them. And I went to University of Geneva, and that's when I showed them all of our stuff, and I showed Fermilab and everybody at the same time. And that was quite a while ago, 5, 6, 7 years ago. Okay, I just want you to know, this is not new to me. This was right after I got out of the Army. I serviced Nike Hercules missile sites when I was in the Army in Alaska in 1968. And I just got into physics deep, real deep. And I realized that there's no possible way that the standard model could work with a gigantic positive core and little tiny negatives. Why wouldn't they just collapse? It was impossible. And this brought me to a real abrupt ugliness with my professor. And anyway, I kept saying there's two types of power. There's two types of intermolecular forces, but they're all dipoles. There's polar molecules, nonpolar molecules. Transfer of energy is from light to atomic vapor. That's all it is dipole vapor. Little tiny particles of dipole vapors. They're everywhere. And even CERN, Fermilab, Don Lincoln says it's called the quantum foam. That's all it is atomic vapor. It's everywhere. I said, okay, therefore Rutherford's atom was wrong. And I didn't just do it one day and say, that's it, I'm done with it. I did this I did everything that they wanted to see done and showed them that everything was wrong. Well, I couldn't really show them it was wrong. I just said, here's my take, here's your take. My take is better. And it was. I went through all their rules and all their different formulas and light energies and chemistry and ions and isotopes, and it was, and it's, I got a lot out of it, yes, no question whatsoever. But at that point I was sort of, like halfway accepting it, but I realized it had to be dipoles. I just couldn't put my finger on it. Now I got it. You see this? I'm not just running my mouth and claiming things that aren't true. CMOS detector system developments for LHC detector. Large CERN will upgrade a major upgrade to increase its instantaneous luminosity. All that is just like taking a cell phone pictures. Same thing, upgrade and performance studies, CMOS, 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 all the way down. And like I say, we were doing this 2015, and I showed them all about this. And they seemed interested, but that was about as far as it got. And then I saw they shut down to upgrade, and I see they're doing the CMOS upgrade, and they focused. Because I said, all you got to do is focus it and then put a cell phone on there and see it. You can see them. And I showed them the articles, I showed them everything. I showed them the particles, I showed them the whole 9 yards. But they're invested in proton smashing. A little bit different situation. And it's not necessary. I know the things I say sound extremely braggadocio, but this is true. This is CERN, high luminosity. Exactly. How is luminosity? What is it? Luminosity is the measure of the number of potential collisions per unit of the surface over a given period of time. It's an essential indicator of the accelerator's performance. So they want to measure luminosity. Now listen to this. They put in focusing magnets, more powerful focusing magnets with new optics. They're doing all the same things that I told them to do. So I don't care if they did them because I said to or not, they're doing them. And they just came back online a few months back, really. It says the new, more powerful superconducting quadrupole magnets will be installed on either side of the ATLAS and CMS experiments to focus the particles before they meet. Exactly. That's exactly what we do through the Venturi. And I showed them, and they were interested, but that's as far as it got. Okay, my friends, this is Teapot Apple II Q House atomic bomb effects. And they have houses, and I think they're like not quite a mile away from ground zero, which means the bomb goes off, and then a short while after, you'll see this house actually burn and not move, and then it'll go flying. And that's because there's two different particles. One has no mass, but it burns, and the other has all mass and no burn. All right, so don't forget, this is atomic central. All right, so here it goes. They're going to blow that house down. All right, huff and puff and blow that house down. The first thing that's going to hit is the white particles. You see that? There's nothing but the white particles, and it just burns it up. That's all. Didn't move anything. Just a burn. So there's no mass to that, to speak of, pushy mass. Then the blacks hit, and boom. Now watch, it'll turn around and come back because they want to come back to that black. The black will be... All right, everybody asked me about the Venturi. I've shown it 100 times. It's so simple, it's just unbelievable. Well, this is exactly identical to what created these pictures back here. I didn't do those. Rod did these because he's so good at it. But I have exactly the same equipment. I did some, but but this is all it was. Galaxy S3 phone. This goes back from 2014, and this is a Bosch GLM 15 laser. He had one for millimeters or something, because he's not in Australia. And then he just put two finishing nails right next to each other, side by side, which created a single slit, and he shot the light right through that single slit. So what are we looking at here? Here's really what we're looking at. Hold on one second. Here's my marker. all this is light coming in, and the black balls are this size, let's say. You know, they're smaller than that, but that's okay. What he has is two pins here. There's so much glow here because it's so brilliant, it obscures where pins are. But here's where the pins are, right here. There's a pin right here, and there's a pin right here. All they are is these little finishing nails. And the white can squirt through, the black can't make it. So the black gets away, and the white is literally squirted through by the blacks concussing. They're solid, they're like bowling balls. Bam, 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 bam. And it never stops. It just continues on forever. As long as you're pulsing laser, you're going to get that fission, and then you're going to get fusion. But in between, you should be able to get a hell of a lot of energy. Okay, I take zero credit for any of these pictures. This was done by another guy, Fabien Boulay, which I lost track of too. He did fabulous work. He must have had some kind of a different phone because he got more squared pixels. Now, although, here's what happened. Rodney said, and again, I didn't do a lot of this. I did some terrible, I'm no good at it. Some people are good at things, other people aren't. I'm not good at it. So, but what Rodney did was he used a selfie, he said. And here's the way he did it. This is basically what he told me. He put it basically right up to the Venturi, or right in this area somewhere. And, well, the one that Fabien did, he did two at a time. He did other ones one at a time, I think. But he put a green one right above the red one. See the green coming out on the red? That's what he did. Same thing, the pins, same kind of pins. That's all. Simple stuff. Very simple. And then, like I say, I don't know what Fabien had. This was only a few years ago. But watch what he did with enhancing the stuff. Absolutely fabulous. But this was, you can see how dim the red is. And you see, remember I told you the barrel rolled? This is the only time I've ever seen this happen. See him spinning this way? That's not supposed to happen. And the green is doing it too. And the reason it's happening is, as I can demonstrate right here. Alright, you've got the red one and then you got the green one. And then when this one comes in, it's going to push, like, it's going to push these particles and they're going to spin in circles. But only because of the concussion of one being so much more powerful than the other, and it's going to spin it as it pushes past it. And that's not a normal event. You're not going to ever see that because both of these particles are accelerated at this point, and they don't normally accelerate like this without going through a Venturi. All right, so this is an unusual event. Very, very rarely you're going to see that. Anyway, this is what Fabien did, but he did much more than this. Where do you see the other ones? Okay, that's Fermi point particles, which I showed you, and here they are right there. Now, this is Rod. That Rod took this picture. Now, here's what happened. Fabien took Rod's work and enhanced it, because Rod had literally thousands of pictures of different particles and all kinds of things. It's just stuff you could never even imagine. Now, but even the green, the blue, the red, they're all exactly the same particle, only they have different spin characteristics, which is the speed that it comes out of the crystal for the laser. Now, so what do we have here? Look down here. Remember, this is getting charged up because the impact here. This is getting dimmed down, and eventually that'll go, and I mean when I say eventually, instantaneously. But look down there, you should be able to see those little red particles right at the bottom. And that's because it's going forward and concussing with them. And it has to push them out of the way. So they're going to glow. It's going to glow as well. Anytime you have push or shove, you have a region of glow. I can't remember the name of the law, Kirchhoff's law or something like that, which says that you just can't, two particles, two surfaces cannot touch. They cannot touch. They get only to a certain point, and they're done. They can't touch. Okay, I think I showed you quite a bit today, but there is a lot more. Now, don't forget, most people have a cell phone, a smartphone, and a lot of people even have these little lasers, which all you need is a laser and a smartphone, a couple of nails to make a Ventura. You may want to do something else with all kinds of different architecture you could make, but the key is to keep it very close and tight so that only the white squirts through. Now, we're going to be going through all of the atomic model, my take on it versus their take on it. Like I said, I don't know if I talked to you about Coursera, but that's the way I do things. I go to these classes at Coursera. These are all my claims. I think I might have shown you all this stuff. But anyway, we have to go through this in detail. And I'll go through each little chunk that I've gotten in here, and we'll get down to what the atomic model looks like and why you get different colors when you look at something that's hit with the same light. Okay, all of this is hit with the same light. Why do we have all different colors? Why? Think about it. We're going to do some deep research into the atomic model and why we see the things that we see. And that right there, my friend, is light accelerating. It proves the wave and the particle. We've seen the tau, the photon, and everything, 100%. All the Higgs fields, we've seen them separate, we've seen them come back together, we've seen them actually fuse back together. So, time to take this seriously.